Hi, my name is Ochre. This video is about the world of pigments and the secret of Ferrari Red. This is a picture of pigments in different colors. There's a difference between a pigment and a dye. A dye is a soluble substance. Pigments are not soluble, they have to be suspended in a medium. This is how car paint works. First layer is the primer. It improves the application of the paint. The second layer is the base coat, which contains the pigment. And the third layer is the clear coat, which gives resistance against UV radiation and scratch resistance. The most used white pigment is titanium dioxide, TiO2. It is used for paint, plastics, papers, medicines, and it is a food color E171. This is a picture of the last step of the Azo Coupling reaction that is used for the synthesis of Azo compounds. This compound at the left is the pigment yellow 12. Azo compounds are very cheap because they are made, they are derivatives of the basic chemical aniline. The diazonium ion connects to the carbon atom here of two molecules, and this gives you this pigment yellow 12, which is used for lacquers, printing inks, plastics, and rubber. This is another yellow pigment. It's pigment yellow 53. It's oxide of nickel, antimony, and titanium dioxide. Pigment yellow 53 is used for plastics, ceramics, and cement. This is the structure of Indian yellow. It is a salt of dioxantic acid. This molecule has a fluorescence and a deep color. It is used for in paintings, and its origin is India of the 15th century. This is ochre. It's iron 3 oxide hydroxide. It's also called limonite. Its basic color is yellow, and with clay and sand you can make different colors like orange and brown. Ochre is mined since at least 2,500 years. This is an image of a horse from Lascaux caves in France. It is made with yellow ochre by Cro-Magnon humans 17,300 years before Christ. This is cadmium orange. It's a mixture of yellow substance cadmium sulfide and red substance cadmium selenide. It is temperature resistant and is used for paints and plastics. And cadmium selenide is also a semiconductor. With different concentrations of cadmium sulfide and selenide, you can make cadmium red. This is the structure of alizarin. It's 1,2-dihydroxyanthraquinone. It is, can be found in the madder plant together with purpurine and pseudo-purpurine, and it was used as early as 1500 before Christ. Alizarin is also a pH indicator. Acidic medium it is yellow, at pH 6 to 12 it is red, and above 12 it is blue. And you can see in this structure formula the basic principle of organic dyes. These are big conjugated pi electron systems. They contain a donor group and an acceptor group. In this case, the acceptor group is the carbonyl group, and the donor group is the hydroxyl group. Another compound, quinacridone, called pigment violet 19, replaced alizarin in 1958 and has fluorescence. For fluorescence, you need a molecule without big rotating parts. Quinacridone is used for organic cells and organic solar cells and as semiconductor. And you can again have a conjugated pi electron system. The donor carbonyl group and amino group is the carbonyl group is the acceptor, donor group is the amino group. This is dragon's blood. It's a red resin from plants like the Dracaena draco. A resin is a substance that can be polymerized, Dragon's blood is used as dye for perfumes and medicine, and was already known to Arabs and Greeks. This is the earliest Azo dye. This was discovered in 1880. That's Ferrari Red. This formula shows you the reaction of the Azo coupling. You need a derivative of aniline. In this case, it's para-nitroaniline. Para is position opposite of the amino group. Then you need sodium nitrate and sulfuric acid. This gives you the diazonium ion, which connects to this position of beta-naphthol. And you get back the proton from the sulfuric acid, and product is Ferrari Red. This is vermilion. This powdered cinnabar, mercury sulfide. It's toxic. It was first documented in 8,000 to 7,000 before Christ in Çatalhöyük, which is in Turkey. And it is also described in the book De Lapidibus of Theophrastus from 371 to 287 before Christ. This is a very important pigment, green pigment, chlorophyll. At the right you can see the formula of chlorophyll A. There are different variants. And photosynthesis was invented by nature 3.2 to 3.5 billion years ago. Life on Earth is at least 3.8 billion years old. And photosynthesis is this reaction of 6 carbon dioxide plus 6 water, which to 1 molecule glucose and byproduct oxygen. This reaction gave Earth its atmosphere of 21% oxygen. This allowed formation of the ozone layer, and life was able to come from the sea, from the ocean to land. Chlorophyll molecule has several jobs. It functions as a light collector and as a charge separator, which provides the electrons for this photosynthesis reaction. Chlorophyll is today used as a food color, E140, for example, for pasta or for candy. This is a malachite green. Can be a chloride or oxalate salt. The structure is a triaryl methane dye. Color comes only from the cation. It is used as a dye and antifungal drug, and it is antibacterial. And again you have this principle of conjugated pi-electron systems with a donor and acceptor. Chromium oxide, chromia green, is also a green pigment. It was first produced in 1838 in Paris. It is used in paints, inks, glasses, and for polishing. This is indigo. It is used more than 5,000 years ago in East Asia, India, Egypt, and by the Maya. It was extracted from plants, which made it expensive. This changed in 1901 when the flicker synthesis was invented and the mass production started. And indigo is the compound that gives genes its blue color. And again, you have this principal donor and pi system acceptor. Acceptor group is the carbonyl group, donor group is the amino group. This is ultramarine. It's powder from lapis lazuli rock. Its main component is lazurite. It has a complex formula. The blue color comes from the ion S3-, which is a radical anion. It was first used in Afghanistan in the 6th century. Today it's used for wall paint, makeup, and papers. This is Prussian blue. At the right you can see its structure element. It is an iron cyanide compound. This is a good example of how Lewis acids and Lewis bases work. The bigger iron 2, is a soft Lewis acid. The smaller iron 3, is a hard Lewis acid. The carbon side of the cyanide ion is the soft Lewis base, and the nitrogen side is the hard Lewis base. That's why the hard Lewis base connects to the hard Lewis acid, iron 3, and the soft side with the carbon connects to the iron 2. Prussian blue was the first modern synthesized pigment. It was invented in 1706 in Berlin, that's why it has this name. It is darker than ultramarine, and it's used in paints, textiles, and in medicine. This is phthalocyanin blue. It is a bright blue color and light fast. Its industrial production started in 1930s. It is used for ink, shampoo, soaps, sunscreen, toothpaste, and as a catalyst for redox reactions. This is carbon black. It's furnace black, also called pigment black 6, elemental carbon. It can be made by an incomplete combustion of, for example, coal or tar. It is used as filler in tires. This gives tires protection from UV light and durability, and it is able to draw heat from other parts of the car. And carbon black can be used for plastics, ink, and paints. This is a modern new pigment. It's called Vantablack. Vanta stands for vertically aligned nanotube arrays, carbon. It was developed by Ferrari Nanosystems in 2014. It is blackest known pigment, and you can see in the picture it's really black. It absorbs almost entire visible light. Since it absorbs stray light, one potential use is for infrared cameras. You could, for example, use this Vantablack for future space telescopes. This is a BMW G06 at the IAA. That's an international motor show in Germany. This picture is from 2019, and it shows that this is just for demonstration. You shouldn't go outside with this car because that's not the plan. You don't want to be overlooked in traffic. But it shows you the potential of this new pigment. There's one thing special about the Ferraris, and that's the red color, red dye. At the right you have the structure of this compound. It's called DPP, diketopyrrolopyrrole. And again, this is a conjugated pi electron system with donors and acceptors. And this is the basic structure of Ferrari Red. It has a high resistance to photodegradation. So normal car paint gets darker over time, because this UV radiation from the sun degrades the organic compounds, and you get brown degradation products. The DPP molecule is also attacked by the sun, but its degradation products are colorless, which means the pigments over time shrink a little bit, but that doesn't change the color. So that's why this Ferrari will keep its beautiful bright red color, and that's the secret of Ferrari Red. That was today's video about the world of pigments and the secret of Ferrari Red. Thank you for watching. Have a nice day. Bye bye.